We are recording. I'm going to leave it on the camera because I'm about to, sorry. Okay, we're about to look at some particular examples. Okay, so switch over to the screen here. So here we're looking at the collection of exercises at the top of page 5. We've already done the question 1 at the bottom of the previous page. At the top of page 5 here, we've got a collection of statements, and they all fit the form of what we would like to do proof by induction on. Okay? They are all statements that are indexed by the positive integers. Okay? So let's have a look at this. First one. I'll do this out as an example. Okay, so this first one is a statement that for every integer n greater than or equal to 1, when you add up the square of every integer, so 1 squared plus 2 squared plus 3 squared plus 4 squared, add them all the way up to n, what you get is a cubic polynomial, and in its nice factorized form, that is how it appears in its factorized form. Okay, so this is what we want to prove, and it clearly looks like a good candidate for proof by induction. It's a nice clear statement, a summation formula, and there's a different formula for every value of it. Collection sections. Okay. So proofs by induction, they always proceed first by considering the base case, n equals, which in this case is n equals 1. Normally, this is just, as I said, just a case of confirmation. Just examine what the thing says for n equals 1, and just confirm that it is indeed true. So if we're adding up the square of every integer beginning at 1 and ending at 1, well, that is just 1. 1 squared, 1. And let's have a look at this formula here. 1/6 of 1 times 1 plus 1 times 2 times 1 plus 1. So it's 2 times 3 to 6 divided by 6. Clearly, you don't need to. It's just simple arithmetic shows that this statement is true. Okay? So it is indeed true for n equals 1. It's a valid formula. It makes sense for n equals 1. Now we need to prove the linking step. Okay? And the linking step is an implication. So to prove the implication, we got to assume the left-hand side. So the implication we're trying to prove is P of k implies P of k plus 1, where P of k means this summation formula with the n up there replaced by k. So in order to prove this implication, we've got to assume the left-hand side, and work on it, and try and show that the right-hand side is true as well. So we make the assumption that the summation from 1 up to k, j squared is what should be 6 of k times k plus 1 times 2k plus 1. Okay, we're not proving that. We're assuming it. We're pretending it's true. It is true at least one time for k equals 1. We're going to loosen that and just assume it's true for some k. For a value of k greater than or equal to 1. True things when especially when you're expressing yourself and communicating mathematics, you want to make it very clear, what the status of these statements are. Okay, so it's clear from what I've written that this statement here is an investigation of the formula when n equals 1, and it's a pretty simple case, 1 equals 1. But this statement here, I've made it very clear to the reader that it's an assumption I'm making. I'm not claiming that this is true. It's a clear assumption. And so these bits of English that I'm putting with the thing are an integral part of the argument. If you've cut out that sentence there, if someone comes along and tries to read the work, they see a simple kind of arithmetic statement up here, which they can see is true. And then they see a statement here floating in the middle of the page. And am I asserting that? Am I claiming I proved it? Am I making an assumption? Is it part of a longer argument? They don't know. Okay, so the explanations are important, are just as much a part of the thing as the actual equations. Okay, so now we try to deduce the formula for n equals k plus 1. And we'll just go ahead and try and prove it directly. So we'll begin on the left-hand side, try and move through a bit of manipulation, and end up on the right-hand side, moving through equations all the time. So we put down what we want on the left-hand side. We want the sum from j equals 1 to k plus 1, j squared. And we're going to work with this. This is kind of what I was, so a trick or device or way of presenting it to help us, because we're going to have to do some manipulation here, but we already know where we need to end up. We want to end up with the correct right-hand side of the statement when n is k plus 1. So we already know that if I'm going to be successful in my chain of equations, there's a little bit of judgment or art here to judge how much space to give yourself if you want it to look nice on the page. But I reckon, well, let's see how I do. The right-hand side I want is a half times k plus 1 times k plus 2 times, what goes in the end? What's the third quantity?
2k plus 3.
2k plus 3, yeah. So this quantity here, where n is replaced by k plus 1. So you can see it's 2 times k plus 1. 2k plus 2, and then an extra 1, so it's 2k plus 3. Everybody clear that this is the result we want? Yeah. There's a big gap in the middle. Okay? So we want to build the bridge from this side to this side. Okay? And our material for building the bridge is fundamentally this assumption here. That is more or less the bridge that's going to take us from there to there, with a little bit of extra stuff, which will just be hopefully just some algebraic manipulation. But the benefit of putting down the destination to begin with is that will guide us in the manipulations that we need to do. Okay, so how do I make some progress? Well, I want to use the assumption. So how do I use this to manipulate this? Well, the observation is that these two left-hand sides are almost the same. This says add up a load of squares. This says add up a load of squares. All the squares you're adding up here from 1, j equals 1, j equals 2, j equals 3, all the way up to k, they're all involved here as well. But there's just one extra term here, because we include the case where j is k plus 1. That's the last thing we add on. We're going to add on the square of k plus 1, which isn't included here. But apart from that last term, these two left-hand sides are exactly the same. So that's going to be our way in. And just to make it clear to the reader, and of course, the reader includes yourself when you look back at these notes in the future. So even though you're making notes to yourself right now, you still want to make them complete and put in all the explanations and show what's happening. Because when you come back to these, you want to be able to read it again and understand it. So this sum, so what we were explaining there is this left-hand side here, it's equal to this, almost. And then it's just the little correction we have to add on, which is the square of k. Okay, this here is the last term that's added on here, that forms part of that. Now that seems very good, because we've brought in we've been able to introduce the left-hand side of the assumption. And then, so it's clear what I'm going to do next. What I'm going to do next, because I've gone to the trouble of making this assumption, I'm going to replace this sum here with the right-hand side. Because after all, look, I'm trying to get to some kind of a polynomial in K. It's a cubic in K, this is a K times K times K. It's a cubic polynomial in K. I've only got a quadratic so far. But once I replace this with this thing here, well, that's a K times K times K. So that will make it into a cubic. So it looks good that I'm going to be successful. So I'll have a cubic, trying to make it look like a cubic. Hopefully they'll be the same. That doesn't need any more justification, I think. We're just working with the definition of the summation symbol. I think that's clear. The next step is using the assumption. So we've got 6 times k times k plus 1 times 2k plus 1. And we've still got this k plus 1 all squared. And this here is by the assumption. By the assumption above. Only one assumption, a few lines above, it's clear what I mean. So you can all, I want you all to appreciate how that's good progress. But of course I was guided by that because I'd already written down the destination, so I knew where I was going. From here on, it'll be just going to be algebra. It's not immediately obvious that this polynomial is the same as that one. I just, you know, there's no reason to believe me if I just say they are. We want to see that. We want to demonstrate this. Well, start comparing the two. We notice here that this one down here, one of the features is that it has a factor of k plus 1. We can already see that we've got a k plus 1 factor in each part. So straight away, we could make this look a little bit more like this by taking out the k plus 1. And that's a pretty straightforward step that won't need too much justification. We take out that k plus 1. We've got k into 2k plus 1. And this is k plus 1 all squared, so there's k plus 1 left. I mean, maybe I could justify that by just putting the word factoring there. Remind myself what I'm doing when I come to read this again. Okay, it's good. We've got a k plus 1 factor. What other factors do we want? We want a k plus 2 and a 2k plus 3. Okay, I don't see k plus 2 or a 2k plus 3. I also want a factor of a sixth. Well, I see a sixth here. Of course, I don't see a sixth there, but really there is a sixth sitting there, isn't there? So I can pull out the sixth as well, which leaves behind here in the first term k times 2k plus 1. What's left behind? What's left behind here when I take the sixth out of it? Sorry? No.
6k plus 6.
6 times that. See, you have to see where the sixth is. Now, you think I'm talking nonsense because there isn't a 6 there, but there is a 6 there, isn't there? It's a 6 over 6. It's 1. So when you take out the factor of a sixth, what's left behind is 6 times that. So what's left behind is 6k plus 6. Okay, this is good progress. I've got a sixth, k plus 1, got a sixth, k plus 1. Well, what I need then is k plus 2 times 2k plus 3, which is a quadratic polynomial. What I've got in here is a quadratic polynomial, so k squareds and some lower k's. So maybe just multiply that out, have a look at it, and hopefully it's going to factorize the required thing. So it's 1/6 times k plus 1, and that's 2k squared, plus k, and then another 6k, so 7k, and plus a 6. Does this quadratic factorize into k plus 2 times 2k plus 3? Well, yeah, it does. You multiply these two, you get 2k squared, you get 3k, 4k, gives you 7k, and you get 2 by 3, which is 6. So yeah, that is just another very simple factoring. So I'm just doing quick factorization. I just split into 3 steps, just taking out one factor each time. I have fairly well justified all these equations. But of course, the single equation I'm interested in is the overall one from the left-hand side at the top to the right-hand side at the bottom. All the middle stuff I really lose interest in for the moment. I've established this formula that I've put a red box in. And that is, what is this formula here? Well, when you compare it to the problem we're working on, this formula in the red box there, from start to finish, is exactly P of K. Isn't it? The summation formula for n, the upper limit is this k plus 1, and the right-hand side is in the required form, as suggested by the formula. I've arrived at it, I proved it. How did I prove it? Well, I proved it based on this assumption. So that is a proof of this whole statement here. It's a proof of this implication. This thing implies this. You make this assumption, you work a bit with it, you use the assumption, do a bit of algebra, and you get the right answer. So we tried to deduce the formula for n equals k plus 1, and we've done it. Remarks like that help the reader know, okay, they actually have done what they've done, and remind you when you're looking at it later on. And so now we can say, by the principle of induction, formula is true, formula is interest, when we put in the green box at the top. Formula is indeed true for all integers n greater than or equal to k. In a number theory course, 99% of the time, the objects we're talking about are integers. So I won't always write down the integer n greater than or equal to 1. It's understood, unless I state otherwise, any of these n's or k's and so on, they're all integers. It's a standard order that these things are integers. Okay, that's good. You should appreciate that the framework there, the structure there, is very much the same as the structure in the example I did at the end of last lecture. The algebra is a bit more involved, because the nature of the formula was slightly more complicated, but it was essentially the same kind of argument. Any questions at all about it? Any of these steps that you're unsure about, or why did I write it like that, or any queries? Yes?
So the outcome we have fine. How do you know it's going to be
So going from here to here?
No, from before you know that, you just mean what?
Oh, so why did I put that down to start? So the reads, yeah, so when I wrote it down, I wrote down this, and then straight away I wrote down that. So what I was doing, this is the formula we're trying to establish. So my left-hand side I put here was this left-hand side when n is k plus 1. And I'm trying to prove that this is true when n is equal to k plus 1. So what is the right-hand side that I'm trying to get to from here? It's 6 times k plus 1, k plus 2. And 2 times k plus 1 is 2k plus 2, plus the x one is 3. So that's why I put that down there in the box. And of course, you can see the utility of putting that in the box. If I hadn't put that there, right, then when you get to this stage up here, you might be a bit lost about where to go. I mean, this polynomial here, there's a number of things you can do to it. You can multiply it all out in a big long cubic. You can rearrange it in all sorts of ways. But there's only really one set of ways of reorganizing it that's useful. It's the set of ways that take you towards this fully factorized expression. So it helps, if you do know what the conclusion should be, very much helps to put it down on the page, because you know where you're going. Okay. Okay, so what should we do? Shall I give you a few minutes to work on it together? See if you Get it out, and then we'll put it on the board. So this next one, everybody finished with that page? So how do we go with that next one? Question 3. Or if one of the other ones is calling to you, feel free to work on one of the other ones. But in a few minutes, I'll do out a solution to question 3. Any questions that you got in the meantime, feel free to ask, and do indeed work together. Question 3 is my suggestion.
I did some of these last night, but I got stuck
Cool.
on 6.
Yeah, so 6 and 7 are slightly different.
Yeah.
Yeah, so all the, if you, once you get the approach going, you can reel off all of these. So 6 and 7 are inequalities.
Mm-hmm.
In some ways, that's harder, you see. When you're trying to bridge that gap with equations, it's quite restrictive because each new step you put down has to be equal to the previous thing. So there's very, very few things you can put down if it has to be equal to the thing that came before it. Whereas when you're trying to establish an inequality, there's a lot more choice.
Yeah.
Because if you're trying to say that this expression here is bigger than this one, so you make the assumption when n equals k, then you put this down raised to the power of k plus 1, and you know you want to prove that it's bigger than this thing, with n equals k plus 1, but then that's a whole lot of freedom, because you know that what you have to do is you have to make the thing smaller each time. You're trying to prove the left-hand side is bigger than the right-hand side, so you want to shrink the left-hand side down until it looks like the destination that you're trying to get it to. But there's many more ways to do that. You can shrink it a lot, you can shrink it a tiny bit, or you can hold it equal, just re-express it as something equal. So you will find those a bit more challenging.
Right. Do you still do it in the same way?
Same overall framework, yeah. Base case, make the assumption, and then you see you can put down. So, rather than just give you the answer straight away. So you'll verify the base case. You'll make the assumption, but the assumption now will be that this thing raised to the power of k is bigger than or equal to the thing on the right hand side. Then that's your assuming p of k. Then you want to try and prove this. So here you have that expression in brackets raised to the power of k plus 1. Don't put an equal sign yet. But at the bottom, you've got whatever the right-hand side is. Yeah?
Right.
And well, what are you allowed to do on the way from getting to here then to here? You're allowed to pass through equations or to make the thing smaller in the next line, to reduce a greater than equality. What you're not allowed to do is to make the thing slightly bigger, because then you lose control about whether this thing at the top is bigger than the bottom.
Right.
So you can rewrite it and keep it equal, or you can shrink it a bit. And you want to do it in such a way such as the expression you end up with is the one you have down here in the box. So still approach it in very much the same way.
Right. Okay.
Yeah?
Yeah.
Does that help, or give you some?
Can I show you what I?
Yeah. Okay, yeah. So show me the statement. So it's this thing. It's 1 plus a half raised to the power. The base case 3 over 2, 3 over 2. Fine. Assume this. Okay, then you go in n plus 1. So you go this.
Don't really know.
Why did you put down here?
I don't really.
You don't sound very confident in it.
I did. 1 over.
I mean, this looks good. This looks good.
I put that there. Is that wrong? I put that there and then I did that.
Is this an addition?
Yeah.
Well, that kind of looks kind of wrong because, I mean, this is raised to the power.
Yeah.
This is all these brackets multiplied by each other. If something's saying it's plus 1.5, that looks kind of wrong.
Yeah, I think it's wrong.
But the idea is replace. Yeah, you do have to use this. So this almost looks like that.
Yeah.
But what exactly is the relationship of this to that?
Do I use that?
You will.
Is that plus something else? So.
Keep saying plus.
Oh, no.
Plus is the. See, we're not talking about plus. We're talking about multiplication.
Oh.
If you've got this and you want to make it look like that, what do you have to do to that? Mathematically, what operation? Multiply it by another one of these factors, and that raises the index by 1.
Okay.
So you can start with this, split off one of these brackets, and what will that leave behind? It will leave behind that bracket raised to power k, which is exactly this. So then you can make use of the assumption.
Yeah, okay.
So you just need to fix this up.
Yeah.
It ain't plus, it's
Yeah.
multiplication. So you check the best case. You assume it's true for n equals r. Now you want to try and prove that the formula is true for n is k plus 1. What does that formula look like? With the left hand side, j plus 1.
That's just what you should. So you've already worked out
It's like this. Instead of
k into that, you get k squared. K plus 1 into that. And you already know what that is, because you wrote there.
Well, that equals
K squared plus 2.
We're going to try and work on this and develop it and make it look like the right hand side. You can take this, you can try and turn it into a square. That's the. Now you've got Well, yeah, that's the question you have to answer. But it's this is the assumption. So this summation here, how do you introduce this? Yeah. Well, this summation is all contained in this. This summation is this one here has got one more term. So you want to separate off that last term. And then you'll be able to introduce this case squared. So have a think about that. Well, it's k squared plus it's the formula 2j minus 1, where j is replacement. So it's not k plus 1. Have a look at it and think about it. Any other questions, queries? Here's where it helps to put things what you can do. Why are you trying to turn this into? Because the very last well, it's when you substitute to know that. So
Oh no, yeah. Oh, it's the kind of thing that.
Okay, I'll do that one out in the board now in just a minute. Some final.
Yeah, it's near the big things.
Well, does it look like street one? Oh, this is actually how did you get it to square? Take this one. Take this one. So you give yourself a long Yeah, this is what you're trying to do. This is here. And start off with this expression here. Yes. I'm effectively
Yeah, I know that's the end. So I said, if I wrote that first and then worked out, or should I have written this? I'll get home like.
Yeah. Well, as long as
train, I get when we get there at
the main thing you're trying to do is establish.
or 1:15.
So whether you do it from left to right, or whether you start off with that right hand side and work on it to the left hand side, whichever way you do it is fine. But you just got to be clear in your own mind which way you're doing it. And avoid the traps, because if you're not clear to yourself or the reader, are you starting with the left position or right, or are you starting with right and left? The danger is you end up kind of going in a circle. You kind of assume the left and then you wander around a bit, and then the right side just comes up. That you assume both of them or something. So yeah. But what have you done? You've done pick this one square, squared it out, and you oh yeah, I see what you're doing here. Yeah.
Would it be alright if we put it at the end?
Yeah, but so in effect what you're doing is see, I proved it starting with the left and I went to the right. You just started at the right hand side. You worked, timed it up, replaced it. See, then you've gone back. See, you saw the case squared, you replaced it with the correct hand. But then you replaced it back to the case squared again.
I was trying to do your way, but you've got the case squared.
Let me show. I'll do your way. Here. Wait until you see this. Okay. So this is question 3. This is a really nice formula. So for Okay. If you want to keep working on another problem, by all means do, but we'll just keep the noise down a bit because a lot of people want to listen to this. Okay. This is one of these really nice formulae. It's saying that when you add up all of the odd integers, you get n squared. So 1 squared plus 3 squared plus 5 squared plus 7 squared, all the way up as far as the last odd integer, 2n minus 1. That gives you n squared. So let's do this. We check out the base case. Base case says the sum from j equals 1 up to 1 of 2j minus 1, which is 1. Is that equal to 1 squared? Yeah, of course. Which is true. So now we make, then we've done the base case. Base case is true. Now we want to prove the implication. In order to do that, we assume the left-hand side, we'll work on it, and we'll try and reach the right-hand side. So assuming the left-hand side means we assume that this is true for some k greater than or equal to 1. Inspired by yourself in the front row. What's your name?
Emma.
Emma, in the front row. She wanted to go, well, let's start on the right-hand side, okay? Because I'm trying to prove p of k plus 1. I'm trying to prove this formula up here, where n is replaced by k plus 1. You were exploring, well, you don't necessarily have to start on the left-hand side and reach the right-hand side. You could start with the right-hand side, and I think maybe it even falls out a bit easier here. What is k plus 1 squared? Now here, now I want to be checking its similarity to this right-hand side, which is k squared. Well, they're nearly the same. If I want to expand out that bracket a bit, k squared plus 2k plus 1. That's good, because there is a k squared. And I've just made an assumption about a k squared. I've assumed that k squared is equal to this summation expression. So by the assumption, I can replace that k squared by sum from j equals 1 up to k, 2j minus 1. And I've still got this 2k plus 1 bit. Okay, we're halfway across the gap. We better be sure we keep going in the right direction and we reach the other side. I should have written down here, with some foreknowledge, what is the right-hand side I'm trying to get to? I'm trying to establish this formula where n is k plus 1. So the destination I'm trying to reach is the sum from j equals 1 to k plus 1 of the odd integers 2j minus 1. Okay, there's still a bit of a gap here. I don't want to go back and start replacing this again by the assumption k squared, because that just starts trying to go backwards. I want to keep going on. So I've got a summation expression here, which is almost looks like this one. They look exactly similar, except this one only goes up as far as k, but this one goes one step further, from j equals k, and it includes, and the next step, k plus 1. But of course, there is an extra bit here. So is this bit here, is that the correct extra bit? Well, that's 2k plus 1. This is supposed to be 2 times something minus something. But of course, it's when j is k plus 1. So all we really need to notice is that we've still got this same sum here, just going up as far as k, 2j minus 1. See, that can be rewritten as 2 times k plus 1 minus 1. Okay, normally, you wouldn't rewrite 2k plus 1 as 2 times k plus 1 minus 1, because you're complicating matters. You're obscuring the real value. by making it more complicated than it needs to be. But in this instance, it is the right thing to do. Because I'm trying to express this in such a way that I can see that it can be incorporated into this sum here. Because what are the things you're adding up here? You're adding up 2 times an index minus 1. And now this term here is magically transformed into 2 times a value minus 1. So it exactly matches this pattern here, where the index, j, is taking on the value k plus 1. But that's exactly the last term that's involved in this. If you take this sum here and expand it out, you've got 2 times 1 minus 1, then j equals 2, 2 times 2 minus 1. Keep going, and the very last term is when j is k plus 1, which is 2 multiplied by k plus 1, and then subtract 1 from the results. But that's exactly what is there. So this sum plus 1 extra term of exactly the same pattern, the very next term. So this equation here is now just justified. So here, in this step here, I was using the assumption this last step here, let's say we could, absorbing the last term, meaning this whole thing here, absorbing the last term into the sum. Just an explanation of what's going on there. People convinced by that? That that's a valid proof of this implication? I bridged the gap based on some algebra, dealing with the summation notation carefully, plus the assumption. And the assumption was exactly this on the left-hand side. Then you finish off by just declaring this is the formula, this is the required form. The required form of the formula, n equals k plus 1. And so, by the principle of induction, the formula is true for every element. By induction, true for all elements. We don't have time to do another example. But any last questions or remarks about that one? You see why you did the right thing, but then you went back on yourself.
Yeah.
You replaced it. You went back in the wrong direction. Okay, just a second. So your tutorials on Friday will be with John Borison, cryptography-based tutorials. Next week I'll be taking the tutorials. Now we will have gone through some more stuff on the lecture on Monday, isn't it? But do work on all these exercises here in induction, and in the tutorials next week we can certainly revisit some of these, clear up any problems remaining with these, okay? So that's your homework. Work on all these, at least before the next number theory tutorial.